Alrighty, in this video we're looking at Moivre's theorem. So this is about powers of complex numbers. Now we may remember some rules of SACE, like SACE of 3 times SACE of 4 would just be adding those numbers together. And you can sort of imagine what happens if you did SACE of 3 times SACE of 3, well, you would get SACE of 6, because I would be adding them together. And if I wanted to do SACE of 3, let's say to the power of 5, well, that would just be SACE of, you can think of it like 3 added to itself 5 times, essentially. So 15. And that's what Moivre's theorem tells us. All right, so let's calculate something like this, 2 SACE of pi over 6 to the power of 6. So what Moivre's theorem tells us is that you do the 2 to the 6 normally, and then you're going to go SACE of 6 times pi over 6. So what you get is 2 to the 6, so that's 64, and then SACE of pi. SACE of pi happens to be -1, so that gives you -64 as your final answer there. All right, if you want to calculate a very big power like this, 1 take I to the power of 20. Now, don't get me wrong, you absolutely can do this on your calculator and it will give you the right answer, but quite often you want to know sort of why it's true or how to do it by hand, especially in proofs and stuff like that. So the first thing we need to do is convert 1 take I to polar form. So 1 take I lives down here on the lovely complex plane. There's 1 and there's -1 on the real and imaginary axis. All right, so we need to think about what the modulus of this is. So I might just say let z equal 1 take I. So mod z is going to be the square root of the real bit squared plus the imaginary bit squared, which is √2. And then to get argument of z, we have to use our little trick. So in getting argument of z, I usually like to calculate this angle I call phi, and that is inverse tan of the imaginary bit over the real bit. And whatever that is, we just tend to make it positive as well. So that's what will work out. We can do inverse tan, make sure you're in radians for this as well, of 1 over 1. Those are the two bits, imaginary and real, and you get pi over 4. So that's the angle I like to call phi, and then as a little refresher, we like to leave phi as is if it's down here, make it negative if it's down here, do pi take phi if it's over there, and phi take pi if it's over there. So that's the one we have, we're in the bottom right. So that means that the argument of z is minus pi over 4, just like that. All right, let's come back and work out the rest of our question. So it turns out that z equals √2 SACE of minus pi over 4, and therefore z to the power of 20 we're looking to work out. Well, maybe I'll just actually write it as 1 take I to the power of 20 equals √2 SACE of minus pi over 4 all to the power of 20. So you're going to get √2 to the 20 times SACE of minus 20 times pi over 4. All right, so we can work this out if we look at doing √2 to the power of 20. That's going to give us 1024. And then this is going to be SACE of 5 pi or minus 5 pi. That'll still give you -1, so the final answer is 1024, just like that. All right, moving on, question 3, we've got a really cool one. It's calculating the square root of I. Now, if you actually just try and do this, square root of I on the calculator, it will give you the answer, and it's sort of that nasty number there. We can confirm that this is true. So let z equal I. So therefore z is going to be 1 SACE of I makes an angle up here of pi over 2. That's where the number I makes an angle. So that is pi over 2 there. Cool. So therefore √I, which is I to the power of a half, is SACE of pi over 2, all to the power of a half. So the number out the front, the modulus, goes to a half, and then we get a half times pi over 2, just like that. So if we keep working through that, 1 will stay the same out the front. So we got cis of pi over 4. And if you want to work this out, what it is in Cartesian form is cos of pi over 4 plus I sine of pi over 4. That happens to be root 2 over 2 plus root 2 over 2i. Or in other words, that's what we got on the calculator before. So that's really good news. Geometrically, if you want to think about it like this, I makes an angle here of 90 degrees. If you look at root I, that makes an angle of 45 degrees. Funny about that. So it turns out that the square root of a number is sort of like going to be half that angle, provided the angles were in a nice sort of region to begin with. One other thing that's really cool is if we look at here, for example, this number, which is -1, has an angle of 180 degrees. I'm working in degrees just to hopefully make it a bit more intuitive. We call this number I the square root of -1, and guess what? It's got an angle of 90 degrees, which is half. All right, the other type of question you can get asked is this one here. So find the smallest positive value such that z to the n is purely real. So mod z is going to be root 3 squared plus 1 squared all under a square root, which is root 4, which is 2. And argument of z, since we're in the top right quadrant, is just directly inverse tan of 1 over root 3. All right, so if we do that, inverse tan of 1 over root 3, we're going to get pi over 6. So therefore, z equals 2 cis of pi over 6. Therefore, z to the n is 2 to the n cis of n times pi over 6 by de Moivre's theorem. All right, so basically, if we want something to be purely real, here's the real axis. If it hit this angle, that would be 0. If it hit that angle, that would be pi. This would be 2 pi. That would be 3 pi if we kept going around like that. So basically, we want this to be some multiple of pi. We can actually make it equal 1 pi if we want. So therefore, n times pi over 6, we just want that to be equal pi. Therefore, n equals 6. So if you think about it this way, here is z with the angle of pi over 6. If we look at z squared, that angle is going to be 2 pi over 6 because the angle just doubles. And then if we look all the way out to z to the 6, that angle there is going to be pi. And this is the first one that is purely on the real axis, because you can sort of see that all these powers here have an imaginary bit. They go up and down a little bit like that. So n equals 6 is the answer. If you do want to double check that, you can do this. So you can go, actually I'll show you something quite cool that you can do in a calculator. Let's go through root 3 plus I. We're going to store it in a letter. So we'll store it in z like that. So now every time that I say z, it'll just tell me that. So if I just do all the powers of z like this, you'll see that I won't get a real one. So z cubed until I hit z to the 6. Notice z cubed is 8i, and that should hopefully make sense since z cubed would be sort of like halfway to being purely real. So here's z cubed. If you keep going on like that, you'll eventually get to z to the power of 6, and then that's minus 64. So that's the first one that's purely real, no imaginary bits.